All right. Sorry. Welcome, everyone. So today we'll continue on with our discussion of thermodynamics and potentially kind of finish up the topic. We'll see if it maybe bleeds a little bit over into Monday. All right, so far, what we've mainly talked about, right, are some of our thermodynamic quantities: internal energy, enthalpy, entropy, Gibbs free energy, right? Talking about the relationships for those with reactions, right? How the standard states, enthalpies of formation, things like that, calculating enthalpies of reactions, Hess's law, and such, right? To be able to understand when the reaction is spontaneous, when it's not spontaneous. Right, and now we're going to apply a lot of these concepts to talk about equilibrium in chemistry. And we're first starting off with phase equilibrium, talking about phase diagrams, phase boundaries, and such. And then we'll talk about chemical equilibrium and then electrochemistry. Okay. So when we left off last time, right, we talked about our phase diagrams. Okay, right? You know, your typical like single phase, or not single phase, single substance, one component phase diagram, right? You got your solid, liquid, vapor type thing. Talk about the phase boundaries, right? Today we're going to talk a little bit more about these phase boundaries and the equations that describe them, right? Each, right, in this phase diagram, right, there's some equation that kind of describes how this phase boundary changes as a function of temperature and pressure, right? There's a specific relationship between the temperature and the pressure that governs the shape of this phase boundary, right? Between solid vapor, and solid liquid, okay? And so we're going to talk about kind of those relationships and what kind of determines the phase boundaries and the structure, okay? So again, when two phases are in equilibrium, just like when your reactants and products are in equilibrium, okay, it's related with the chemical potential being the same between the phases, right? So again, here, plot chemical potential versus temperature, right? It's talking about the chemical potential is equal between solid and liquid at this point, liquid and gas, right, at that point, at that phase boundary, okay? Now, just take it as a given here that this change in your Gibbs free energy is related with volume times the change in pressure minus entropy times the change in temperature, okay? And so this type of a relationship tells us, okay, that a change with respect to the Gibbs free energy with respect to temperature under constant pressure. So take the derivative of this equation up top with respect to temperature, okay, and set pressure to be constant. So that subscript P is indicating constant pressure. You don't need to worry too much about these partial derivatives and stuff. I'm just kind of showing you where these relationships come from, okay? And So when you take the derivative of this respect to temperature under constant pressure, pressure is constant, so this term just goes to 0, and you're just left with minus entropy times dt dt, which is just 1, okay, right? So we can write this out. Let's, right? Right, dg equals vdp minus s dt, okay? So I'm going to take the derivative with respect to temperature of that entire equation, if you will, holding pressure constant, okay? So I get dg dt under constant pressure, okay? And then here, this pressure term just goes to 0 because pressure is being held constant, so this entire term is just a constant. Okay, and the derivative of a constant is 0, right? And then the second term, minus s dt dt, right? Under constant pressure. Well, this is just equal to 1, right? So x divided by x, right? So that's just equal to 1, right? And so that change, right, in Gibbs free energy with respect to temperature or constant pressure conditions is just minus the entropy, okay? So what is the meaning of M and GM? Molar, yeah. So yeah, I was about to get there. Thank you, Nathaniel or Nathan. Not sure which one you go by for that. But yeah, so here, so yeah, I was about to get to that line next, right? So here, instead of writing the Gibbs free energy, I put the chemical potential, and to get that, I have to divide by M. Right, this talked about this kind of last time, right? But like, I forget where I used it, but oh yeah, when talking like heat capacity, right? CPM was the heat capacity under constant pressure divided by the number of moles. Okay, so GM is just the Gibbs free energy divided by number of moles, and that happens to also equal the chemical potential. The chemical potential is related to the Gibbs free energy divided by the number of moles, that molar Gibbs free energy. Okay, so whenever you see a subscript M, that means it's just this quantity divided by the number of moles, makes it an intensive quantity. Okay, right. And so this change with respect to chemical potential, with respect to change in temperature under constant pressure, is just related with minus the molar entropy of that phase. So we look here, right? So we see, right, this slope, right, and plotting temperature versus chemical potential. So the slope here is just minus the molar entropy, right? So notice that all these slopes are negative, right? And then we see, right, that the reason why the solid line is more flat while the gas is much more vertical, okay, right? The slope is much greater for gas compared to solid, right, is because, right, the entropy in a solid is much, much less than, say, the entropy in a gas, right? That molar entropy, right? The entropy per mole of a solid is much smaller than the entropy per mole of a gas, right? So the entropy of a gas changes significantly more with temperature, right, than that for solid. And so the chemical potential of a solid is relatively constant with temperature, while the chemical potential of a gas varies quite a bit with temperature. Okay, right? So again, that's what. So the fact that this the slope is related with the molar entropy is why there's different slopes between the three phases, and why they get more and more steep as you go from solid, liquid to gas. Okay. Right? So that's kind of the first relationship we want to talk about today, is how this chemical potential changes with temperature, related with entropy. Okay. Right. Now, at a phase boundary, right, you have to have some certain combination of pressure and temperature to where the chemical potentials between the two phases are equal. Okay, so the chemical potential in the alpha phase, say a solid, right? Alpha and beta here, just like, you know, solid, liquid, gas, whatever, right? Whatever the phase might be, right? So at a phase boundary, those two things are equal, okay, right? So if we're able to somehow solve this equation, right, write out how these chemical potentials are a function of pressure and temperature, and solve for pressure in terms of temperature, right, that would give us this equation that describes our phase boundaries for these single component systems, okay? Right? And the slope of that equation that relates to pressure and temperature, right, will be related with dP dt, okay? Right? So again, the slope of these phase boundaries is, right, change in pressure with respect to change in temperature, right, dP dt, okay? Right? And so, right, if we're interested in that slope, okay, well, we showed how the chemical potential, right, is related, change in chemical potential with respect to change in temperature is related with molar entropy, okay? You can go through a similar thing, right? So if I go back, back to the share, right? So we kind of showed how that, using this equation here, right, equation up top, how we can show how that chemical potential, right, change in chemical potential affects change in temperatures with molar entropy, okay? And you can use this equation to also, right, show the fact that the change in chemical potential with respect to change in pressure, P, right, under constant temperature, is just the molar volume, the volume per mole that a substance occupies, right? And so using that, right, we can say, okay, some change in chemical potential is related with some change in temperature times the molar entropy, and some change in change in pressure times the molar volume, okay, right? So as before, right, we said, right, if we're at some phase boundary and I change the temperature some amount, right, and the pressure some amount, if I want to maintain myself at that same phase boundary, right, this change in temperature times the molar entropy of the alpha phase plus the change in pressure times the molar volume of the alpha phase has to equal that change in temperature times the molar entropy of the beta phase plus change in pressure times the molar volume of the beta phase, right? That this relationship has to stay the same, right? The chemical potential, the alpha phase and beta phase have to remain equal even as I change temperature or pressure if I want to stay on that phase boundary, right? So the main concept here is we're trying to stay on the phase boundary, right? We're saying we're somewhere here on this liquid vapor phase boundary, right? We're at this point, and I'm changing the temperature and pressure some amount, and I want to remain on that boundary, right? So in order to remain on that boundary, okay, these two things have to equal each other, okay? So what I'm going to do is I'm going to collect the entropy and temperature terms on the one side and the volume pressure terms on the other to get this equation here, right? So just rearranging a little bit what's up top. And then when you divide the temperature dt over to the other side and then the change in volume on the other side, right, you have this relationship here, that the slope of these phase boundaries, okay, dP dt, right, that slope on those phase boundaries is related with the change in molar volume between the two phases and the change in molar entropy between the two phases and the change in molar volume between the two phases, right? So delta transition Sm, right, is the molar volume of, say, the vapor phase minus the molar volume, or I keep on saying volume, right? The molar entropy of the vapor phase minus the molar entropy of, say, the liquid phase, right? That would be what delta transition Sf is, right? Delta transition Vm, right, is the difference in molar volume between the molar volume of the vapor phase minus the molar volume of the liquid phase, right? So it's just how does the molar volume and the molar entropy change between those phases, right? So if we go back to these phase diagrams, right, we see, right, for example, the solid liquid boundary is typically very, very steep, right? Well, the reason why that's very steep, right, is the slope of that line is given by the change in molar volume over the change in molar entropy over the change in molar volume, right? The slope of the line, that very steep line, is given by delta S over delta V, right? The change in molar entropy over the change in molar volume, right? Well, the molar volume, right, the amount of space per mole a solid takes up versus the amount of space per mole a liquid takes up is typically about the same, right? As you melt some solid, right, the volume it takes up doesn't change significantly. It changes slightly, right? Water, right, actually the volume decreases slightly as you melt it, right? Most substances, the volume increases slightly. So there's some change, but it's very small, right? And so because that change in volume is so small, that's what causes this to have such a steep slope, right? Because we're dividing by a very small number. You have a very small change in molar volume, okay? And so that's what causes the slope between solid and liquid phases to be so steep, right? Similarly, right, the slopes between the liquid and vapor and solid and vapor, right, are a little bit more gradual, okay? Right, they're not quite as steep, and that's partially due to the fact that the molar volume change between the solid and a gas or liquid and a gas is much greater, right? That a gas takes up a lot more space than a liquid does or a solid does at the same temperature. Okay. All right. So there's this Clapeyron equation, right, can help us kind of understand the general trends in our phase diagrams, right, and what these phase boundaries should look like. Okay. So questions about this Clapeyron equation, interpretation of it? All right. So if I want to look at specifically the liquid-gas transition, right, I have that Clapeyron equation, the change in pressure with respect to change in temperature is related with the change in molar entropy over change in molar volume, okay? Right, using the fact that that change in entropy is related with the change in enthalpy divided by temperature. Oh, here in chat. Oh, what is the meaning of yeah, TRS is transition. So it's the phase transition, say liquid to gas, right? So if you're looking at liquid to solid, right, it's that change in molar volume between a liquid and a solid, right? That boiling or melting, right? Okay. So here TRS is just, again, short for transition, right? For phase transition. So the idea is right, this equation is related with phase transitions, right? And so it's talking about specific phase transition. What is the change in molar volume? What is the change in molar entropy? And what is the change in molar volume for that phase transition as well? I just can't help myself from saying molar volume when I see this SM here for some reason. I don't know. I can't say molar entropy. I made that mistake I don't know how many times so far today. But yeah. So again, this delta S, right, can be related with delta H divided by T, okay? Because at our phase boundaries, we're at equilibrium, right? And again, right, if we want to remind ourselves, right, okay, of that, right, Gibbs free energy is equal delta G equals delta H minus T delta S, right? Well, if I'm at equilibrium, delta G is equal to 0, okay? Things at equilibrium, the Gibbs free energy change is equal to 0, okay? Right? And so at equilibrium, delta G is equal to 0, right? Which again, at our phase boundaries, our phases are at equilibrium, okay? So, right, And if I want to kind of use the notation from before, that's transition, 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 TRS, right? I'll add these TRSs, right? These transition, right? So this Gibbs free energy change for the transition, right, at equilibrium is equal to 0, right? Because at your equilibrium, at your phase boundaries, you can go between, say, solid and liquid or liquid to solid freely, right? And it's not changing the overall free energy in the system. And you have constantly the phases fluctuating back and forth between each other, right? Because neither phase is at a lower free energy, right? So there's no, both phases are stable, right? And so that change in Gibbs free energy between the, say, the solid and liquid is equal to 0, right? It's like Gibbs free energy of the solid minus Gibbs free energy of the liquid, right? That change is equal to 0 at equilibrium at the phase boundary, okay? And so that, and so this entire term here just equals 0. And so I can just solve delta S then is equal to delta H divided by T by just solving right there, okay? So that's where we get that equation here, okay, the delta S is equal to delta H divided by T, okay? So plugging that in, okay, you have this, so it's still this kind of Clapeyron equation. I've just replaced delta S by the delta H and then divided by T, okay? Now here, we're specifically talking about liquid to vapor transition, so we're talking about vaporization. So VAP is for vaporization, right? It's a liquid going to a gas, right? You're boiling something, you're vaporizing that liquid, okay? All right, so that's why vape is there, okay? Right? And again, right here, right, this is an endothermic process. It requires energy to convert a liquid to a gas, right? And the molar volume change is also positive, right? You have a greater molar volume for gas than you do for the liquid, okay? So the slope is positive, okay? And it's not as steep, okay? Right? And if we want to go further, right, and try to kind of roughly solve for what that equation looks like, okay, we'll get what's called the Clausius-Clapeyron equation, okay? So we'll use the fact that for vaporization, right, you have the molar volume of the gas minus that for the liquid. We're just going to assume the volume that the liquid occupies compared to gas is very small, which is a very, very reasonable assumption, right? 1 liter of water, if you were to boil that water or have just the same number of moles of water at room temperature and pressure, so 1 pressure, 298 Kelvin, 1 mole of water, okay, the volume that would take up, it would be, actually, it's not even 1 mole of water is in 1 liter. I forget how many moles. I think it's like 55.555, something like that, 5.55, or 5 or 50 moles. Closer to, I don't know. I figured out. I think it's like 55 or something. So it's like 55 moles of water is in like 1 liter, okay, more or less, right? And if you took those 55 moles and converted them to a gas at the same temperature, pressure conditions, the volume it would take up would be much, much, much greater than 1 liter, okay? And so this difference between the molar volume of the gas and molar volume of the liquid is roughly just the molar volume of the gas, right? It's like taking the difference between 1,000 and 0.1, right? 1,000 minus 0.1 is basically rounded to 1,000, right? And if we assume the gas is ideal, okay, that molar volume of an ideal gas, right, PV equals nRT, can solve for the molar volume, you get RT divided by P. So you plug that in to the equation here, okay? You have dP dt is roughly equal to the enthalpy of vaporization divided by the temperature, right, times RT divided by P, okay? So rearranging that equation, you get this kind of final form here, dP divided by P equals delta H of vaporization divided by R is your ideal gas constant, times dt over T squared, okay? Just a differential equation. You can integrate both sides from some initial to final state. And I'm not worried about requiring you to do that, but If you do it, you'll get this final Clausius-Clapeyron equation. So the natural log of the final pressure over the initial pressure is equal to minus the enthalpy of vaporization divided by R, your ideal gas constant. Now here, right, the enthalpy of vaporization is often given in, say, kilojoules, right, per mole. So your ideal gas constant here that you want to use is the 8.314 joules per Kelvin mole version, not the 0.08206 liters atmosphere version, right? You want the R in terms of joules. So it's, again, 8.314. You don't need to memorize that, but yeah. And then you have the reciprocal of the difference of the temperatures, right? 1 over T final minus 1 over T initial. Okay? And again, this is referred to as the Clausius-Clapeyron equation. And so this equation, right, as long as your vapor kind of roughly satisfies the ideal gas law, okay, and assuming the enthalpy of vaporization is constant, this equation describes, go all the way back here, right, this liquid vapor boundary, right? So this is the pressure temperature equation that describes this phase boundary here. Okay. This is Clausius-Clapeyron equation. Right. And I want to reiterate something because, again, right, it's a very useful thing, especially with liquid vapor boundaries, right? The fact that, right, we often care about when a substance boils, right? And again, when something boils is when its vapor pressure equals atmospheric pressure, and that liquid vapor boundary gives you what is the vapor pressure of that liquid at a certain temperature. Okay? Because, right, again, think of what is the vapor pressure of a liquid, right? The vapor pressure of a liquid is the pressure that liquid exerts, right, in a closed container, okay? Right, so imagine you have a liquid in a closed container, right, that's initially, right, there's nothing above the surface of the liquid. No gas, it's a vacuum above the surface of the liquid, right? Well, atoms that are molecules on the surface of your liquid might escape from the liquid phase into the gas phase, right? They got some kinetic energy, they're moving around. They might get knocked out into the gas phase, okay? And then you continue to have molecules in your liquid phase get knocked into the gas phase, and you slowly are building up pressure above the surface of this liquid, right, which is the vapor pressure of that liquid, okay, until you reach a point, okay, where you then have some of these gas phase molecules going back into the liquid phase because they're bouncing around and they collide with the liquid and they get captured and trapped, right? And this process is occurring where you have liquid going to gas and gas going to liquid until you've reached an equilibrium, right? And then it stops, and then you have some net number of molecules in the vapor phase, some net number of molecules in the liquid phase, right? And that net number of molecules in the vapor phase exerts some pressure, and again, that's your vapor pressure, right? Well, the net change of things, right? Things stop in which I get no more net gas phase molecules or liquid phase molecules once I've reached equilibrium, right, between the liquid and vapor phase, right? And so the vapor pressure is established, right, and that vapor pressure is determined by where the equilibrium between the liquid and vapor lie, okay? And so that liquid vapor phase boundary tells you the vapor pressure of a liquid at a given temperature, okay? And so this Clausius-Clapeyron equation can tell us how the vapor pressure of a liquid changes with a change in temperature. Similarly, right, if we think about boiling temperatures of liquids, right, if I want to know how does the boiling temperature change for my liquid with a change in pressure, right? If I change the external pressure on my liquid, right, how does that change its boiling temperature, right? I would still use this equation, right? I would put the change in external pressures here and calculate the change in boiling temperatures here. Because again, the external pressure, right, boiling temperature is related when the vapor pressure equals the external pressure, okay? And so again, this Clausius-Clapeyron equation can be used to answer kind of both those type of questions, right? What is the new vapor pressure at a new temperature for my liquid, and what is the new boiling temperature at a different external pressure for my liquid, right? So again, like think of you have some, reaction you want to have take place, okay? But you want to try to do it underneath a vacuum, right? Because you want to minimize, you know, uh, something, right? You want to minimize the amount of molecules in the atmosphere dissolving into your liquid and reacting with the reactants in the liquid phase or something like that, right? You want to do this reaction in some sort of vacuum, right? You need to know, is my liquid going to start boiling if I create too much of a vacuum, right? And you answer that question using this equation, right? And saying, okay, if I reduce the pressure, the external pressure on my liquid by this amount, will my liquid start boiling or not, right? So questions about this Clausius-Clapeyron equation, its derivation, its uses. All right, so that was kind of the final point on phase equilibrium I wanted to talk about, right? So the main things with phase equilibrium, right, is just remind ourselves kind of what the phase boundaries are, and then the fact that these phase boundaries are related when chemical potentials are equal to each other, right? To introduce the idea of chemical potentials, okay? When we talked about the Clapeyron equation and Clausius-Clapeyron equation related with the shapes of these phase boundaries and the slopes, okay? So now let's talk a little bit about chemical equilibrium and where, say, this equilibrium constant comes from and things like that, okay? So again, the idea of chemical equilibrium is the fact, right, that you have some mixture of reactants and products when you put them together, that once you've reached this equilibrium, right, there's no net change in the number of molecules or the number of moles in the reactants, and no net change in the number of moles in the products, right? And right, again, chemical equilibrium is a dynamic equilibrium, right? Reactions are still taking place. There's just no net change in number of moles, right? And kind of, if you were to plot the Gibbs free energy of the reaction as a function of, say, how much reactants is reacted, right? So, 0% is reacted over here to 100% over here, right? You'll get some sort of curve, maybe that looks like this blue one, okay? Where you'll end up with some minimum Gibbs free energy that's not necessarily at the products, right? Okay. And that minimum Gibbs free energy is related with the equilibrium mixture of your reactants and products. Okay. Now, let's go with this, right? Hopefully everyone's familiar with the idea that, right, chemical equilibrium is a dynamic equilibrium, right? So I'm not going to focus on that, right? But right, the idea here is again, in this slide talking about this equilibrium mixture. One of the key points here is you're allowing your reactants and products to mix. If you were to extract the products as the reaction's going, the the dashed line is what you would be following, right? The dashed line describes what the overall free energy is for your system, right, as you're reacting some of your reactants to form your products, okay? Assuming that they don't mix. That once you form products, you extract it out, right? You separate it from the reactants, okay? And if you do that, right, you will always get 100% of your stuff forming products, right? Forming, assuming the products are at the lower free energy, right? Whichever one's at the lowest free energy, right, you will get 100% formation of that given enough time. Again, we're not thinking about kinetics and how long it takes the reaction to go, but given enough time, right, your reaction will go to completion and form 100% of whatever the lower energy free energy state is if you don't allow these things to mix. But if you allow them to mix, right, if they're in the same container, same solution, same vessel, right, then the mixing of these things will cause the free energy change to look like the solid curve here, okay, where there's some equilibrium mixture that has some amount of products and some amount of reactants that exist together. Okay. All right. Let me see here. I forget if I have. No. Right. This mixture, okay, is, if you think of potentially, say, ideal gases have a lower free energy when they're mixed than when they're separated. Okay. Right. So, and that's purely an entropy-driven process. Okay. So this mixture term, if things are ideal, is purely entropy-driven. Okay. Now, if obviously things aren't always ideal. If there's intermolecular forces that exist between your reactants and products and things like that in solution, if this is a solution phase reaction, right, then that can potentially cause, right, the free energy change to be lower, the free energy to be lower when some amount of reactants exists and some amount of products and such, right? So kind of depending on kind of your system, what's determining where this minimum lies very much just depends on your system, right? Whether or not the reactants or products have a lower free energy, and then how strong is this interaction of the mixture, right? If it's purely, if you just have no intermolecular forces exist between the reactants and products, right? It's purely an entropy-driven process. Well, entropy would want a 50-50 mixture every time between reactants and products, right? Okay. Now, because the free energy between your reactants and products are different, and because they have intermolecular forces that exist between them and things like that, that also affect the mixing, okay, this equilibrium is not going to lie at a 50-50 mixture, and it's going to favor one side or the other, right? And it's always going to favor the side that has the lowest free energy for the products versus reactants, obviously. Okay. And again, but that chemical equilibrium occurs at the minimum free energy for that reaction mixture, which again is a mixture of reactants and products when they're allowed to be mixing together in the same container. But again, if you don't mix them, you'll just get all products eventually, right? Okay. So let's talk a little bit more about this reaction mixture and kind of show where the equilibrium constant comes from and such. So let's assume I have some reaction A going to B, stoichiometric coefficient little a and little b. Oh, something in the chat here. Sorry, I missed it. Can you explain a little more about without mixing with examples? Yeah, so, for example, if I wanted, right, I think I remember this from like my Gen Chem days or something like that, right? Talking about the Haber-Bosch process, right? Forming of ammonia. I forget what that process is called, right? But H2 reacting with N2 to form NH3, right? That chemical reaction, right? Well, right, in some company, right, wants to optimize their formation of NH3, okay? There's different things that they can do to optimize that formation, right? One of those things is if you just have a big container of, right? So let's pretend draw something here, right? So if I have some big container of H2s, N2s floating around, right? Initially, right, these guys will react with each other and also form some NH3s, okay? In here, okay? Right, right. I have this reaction 3H2 plus N2 goes to 2NH3. Okay, right. So I have that chemical reaction. Okay, right. Now, if this reaction is taking place in a closed container like this, right, right, just based off of entropy, okay, I don't want to have just all NH3 or all H2 and N2, right? Because again, entropy, right, favors more disorder, more random, more different things, right? So based off of entropy, right, if everything was all about entropy for mixing, right? If all that we cared about was entropy for mixing these two guys together, right, I'd want sort of, an equal amount equal amount of H2, N2, and H3, right? Now maybe you aren't able to get an equal amount of all three of those things based off of their stoichiometric coefficients, how much you start with, and blah blah blah, right? But ideally, right, a mixture of all these things, right, that would have the greatest entropy would be an equal number of moles of all those things, right? So if my reaction just cared about optimizing the entropy of mixing, right, I would get roughly an equal amount of moles of all those things, right? And so that, right, is sort of, one of the reasons why when you mix these things together, right, your reaction doesn't just go to completion, right? That this reaction doesn't just form all NH3, but there is some H2 and N2 left in this container because, right, if they're allowed to be in the same container, right, they're mixing together and entropy and such would cause a lower free energy for the system to have some amount of N2 and H2 floating around, right? Even if NH3 is a lower free energy state compared to N2 and H2, right? And so if I'm doing this reaction, what I'd want to do is I'd want to have some type of filter here, if you will, that allowed my NH3, okay, to escape, right? So that while this reaction is taking place, right, I'm getting rid of my NH3s, okay? So then my reaction can keep on going, and then and then I have, now two containers, one with just NH3s on one side and one with the reactants on the other, right? And then if you had something like this, right, the reaction would go to completion, okay, and you'd react all H2s and N2s up to your limiting reagent, right? And you'd form 100% yield of your NH3. Okay, if you or kind of phase separate these things, if you will, between two containers or something like that, right? Okay. And so that's why in solution you establish equilibrium between things and stuff like that, right? Because your reactants products are all in the same solution, right? But if you have some semi-impermeable membrane in your solution that allows only certain molecules to pass from one side to the other, things like that, right? You can phase separate your reactants and products, right? You can force this reaction to go to completion and never establish any type of equilibrium, right? Again, to establish an equilibrium, you have to have a mixture of reactants and products be possible. Okay? Otherwise, chemical equilibrium is never going to be able to be established if I can't mix them together, right? So without mixing, no equilibrium is ever established, and you just always form the lowest free energy state. Does that kind of answer the question? Okay. All right. Right. So, right. So think of kind of the extent of my reaction being 0 when all reactants are present, 1 when all products are present, right? So think of this as kind of the extent of the reaction is like the percent reacted, right? 0% all reactants, 100% all products, right? So 0 to 1. Okay. So based off of that definition, right, I can calculate the number of moles at any given time in my reaction of A and the number of moles at any time in my reaction of B by the initial number of moles of A minus the extent of the reaction times the stoichiometric coefficient of A, and then the number of moles of B times the stoichiometric is the extent of the reaction times the stoichiometric coefficient of B. Okay. And if I think about what is the change in number of moles of A and change in number of moles of B with respect to the change in my extent of my reaction, it would just give me this relationship here, D and A equals minus A d eta, and D and B equals B d eta here. Okay. A and B again are your stoichiometric coefficients in your balanced equation, right? Na naught is the initial moles of A, right? Okay. So Na naught is your initial moles of A. Okay. So I have this is, right, so as my reaction's going forward, right, as my reaction's occurring, some change, as the reaction's going from 0 to 1, right, the extent of the reaction is going from 0 to 1, my number of moles of A is changing according to this equation, my number of moles of B is changing according to this equation, right? And I'm going to define here the free energy change for the reaction as the change in free energy of the reaction with respect to the change in the extent of the reaction at constant pressure and temperature, right? So again, the subscript here is meaning constant pressure, temperature conditions, okay? Well, under constant pressure, temperature conditions, right, that change in free energy, right, the only thing that's changing the free energy as this reaction is occurring is the change in number of moles of reactants and the change in number of moles of your products, right? Because the change in number of moles of reactants times its chemical potential will change, it gives you the change in free energy from the reactant side, and the change in number of moles of products times its chemical potential gives you the change in number of moles of products, right? Because again, the chemical potential is just related to free energy divided by the number of moles, right, of that thing, right? So this mu A is like Gibbs free energy divided by number of moles of A, mu B is like Gibbs free energy divided by number of moles of B, right? So this mu A times change in number of moles is giving us a change in Gibbs free energy with respect to how much A we're losing, and mu B, D, and B is giving us the change in Gibbs free energy with respect to how many moles of B we're gaining, right? So plugging in for what the change in number of moles of A and B are in terms of the extent of the reaction, okay? And then dividing the extent D times eta here, the extent of the reaction onto that side, right? I get the Gibbs free energy change for my reaction is just equal to minus A mu A plus B mu B, where A, again, the little lowercase a is your stoichiometric coefficient, lowercase b is your stoichiometric coefficient, and then mu A and mu B are the chemical potentials of A and B, okay? Right, and those chemical potentials vary depending on the concentrations of A and B and such in the mixture, okay? So those aren't constants, they will change as the reaction's occurring, okay? Right, and so at equilibrium, right, again, at equilibrium, we're at the minimum of our free energy, okay? At equilibrium, right, we're at the minimum of the free energy, okay? So at equilibrium, right, that slope, that change in free energy at the minimum is equal to 0, right? So at equilibrium, this change in free energy of the reaction is equal to 0, which tells us at equilibrium, right, the chemical potentials of our reactants equal the chemical potentials of our products multiplied by their stoichiometric coefficients, okay? And this is true if I had more reactants and more products, right? It would be A mu A plus C mu C for the reactants, if C was a reactant, right, equals B mu B plus D mu D or something like that if D was a product, right? So this isn't just true for, you know, one reactant going to one product, right? If I have multiple reactants and multiple products, I just add in the stoichiometric coefficient times the chemical potential of that reactant or product onto the left or right-hand side, right? The left side is for the reactants, right side is the products, right? Okay. But again, as I was talking about on Monday, right, this chemical potential gives us a relationship between, right, the chemical potential is telling us when equilibrium is established, right? Equilibrium is established when these chemical potentials are equal to each other, right, with a factor of the stoichiometric coefficients thrown in there, okay? Right? So again, this free energy change for the reaction, right, as I'm going forward, goes downhill, it's negative, right? So this is a spontaneous process, right? Once I reach equilibrium, the change in free energy is equal to 0, okay? Right? And no net reaction is occurring anymore, right? If I'm at equilibrium and I want to go uphill, right, to form more products this way or to form reactants back the other way, right, that is going to be a non-spontaneous process, okay, with a positive Gibbs free energy change, right? Okay. Yeah, so delta G being greater than 0 here is saying that the reverse reaction, right? So you know, if I wanted to go uphill here, right, that's not spontaneous, but the reverse reaction going back down towards equilibrium is spontaneous, okay? Right, but yeah. Okay, I thought I had, that's right. So I kind of got rid of that slide, okay, that relates to delta G of the reaction with equilibrium constant. Okay, so we have this relationship here, delta G of the reaction is related with mu A and mu B, okay? And basically, so I'm not going to go into detail in this class, but basically this chemical potential of some compound A is related with its standard chemical potential, okay, at 1 bar pressure and things like that, right? 1 molar concentration, right? Plus RT ln of pressure of A, okay? And so this, using this relationship and then that delta G of the reaction, right, being related with A mu A plus B mu B with a minus sign here in front of A, right? So using these two equations here, okay, plugging this in to this equation here, and then kind of simplifying and such, you'll get out, you'll see, right, that the equilibrium constant that we define for, say, this reaction A going to B, right, is just the pressure of B raised to the B power divided by the pressure of A raised to the A power. Okay? So you'll get out this relationship. So I mean, and I'm not going to go through in great detail in this class, but I just want to point out the fact that the equilibrium constant itself, its form, and the fact that it's only relevant for gases and for ions and not solids and liquids appearing and things like that, right? And its products over reactants rates are stoichiometric coefficient, right? The form of these equilibrium constants that we introduce in general chemistry and such, right, are determined by how the chemical potential of your reactants and products change with pressure, with their pressure or concentration, if it's a aqueous species, right? And so, yeah, so that's where this value of the equilibrium constant comes from, right? And kind of using that, you can get this relationship here, right? So you kind of see, again, go back here, right? You can kind of see where certain things come from, right? From this relationship here, right, you see how you have RTs, right? So how this delta G, right, you can kind of hopefully see, right, when you plug in things, what you'll get is you'll get the free energy change for the reaction. It's related with the standard free energy change for the reaction, okay, which we'll talk about in a second, right? Then minus, plus RT ln of, this would be P B to the B power over P A to A power, okay? Where this delta G naught here is just A mu A naught plus B mu B, right? This standard chemical potentials, sorry, minus sign in front of that, okay? Right? But in this equation, okay, if I take this equation, let me grab my slides, some more paper here, right? So if I take that bottom equation, right, at equilibrium, right, delta G of the reaction is by definition equal to 0, which tells me that the standard Gibbs free energy change. So that superscript 0, right, is again same standard. So 1 pressure, 1 bar pressure, 1 molar concentration type things, right? Elements, molecules are in their standard state, okay? Plus RT, okay? ln, then I'm going to just write this okay, right? Basically this, yeah, right? K here being your equilibrium constant, right, which is related with PB, right, for the reaction, AA going to be B, right? That's the equilibrium constant, so I'm just going to put K here, okay, right? And then you just subtract RT ln of K to the other side, right, to get the standard free energy change of your reaction is just related with minus RT ln of K, right? Your equilibrium constant, right? So you can get that kind of relationship, right? So all of these things kind of come out and come together, right, for free energy, Gibbs free energy, and chemical equilibrium from these chemical potentials and the fact, right, that chemical potentials need to basically be equal to each other between the reactants and products, right, multiplied by their stoichiometric coefficient, right, at chemical equilibrium, okay? And you get out this equation here that relates to Gibbs free energy under standard conditions with the equilibrium constant K, right? Or delta G, naught here, again, is something that potentially you can calculate from tables, or you calculate it using this equation, right? But it's a standard Gibbs free energy change for a reaction, okay? And then K, again, is the equilibrium constant under some current temperature pressure conditions, right? And again, we have that kind of relationship between the two. So kind of questions about this? So we have an example here. So if the temperature, right, yeah, so if temperature of water bath closed system is raised from room temperature to 65 Celsius, and the initial pressure is 35 torr, what is the final pressure of the system, right? So the initial pressure meaning like, right, so it's closed system, just water. So it's the vapor pressure of the water is initially 350 torr at room temperature, okay? So 25 degrees Celsius, right? And I increase the temperature to 65 degrees Celsius, and I want to know what is the final pressure inside this closed container, right? So what's that final vapor pressure of my water, given the enthalpy of vaporization, that heat of vaporization of water is 43.99 kilojoules per mole. All right. So, right, for this problem here, right, we're given kind of this summary of this information, right? At 25 degrees Celsius, my vapor pressure, right, is 350 torr. I'm wondering what is my vapor pressure at 65 degrees Celsius, okay? So to get that, we need to use that relationship between the vapor pressure at different temperatures, right? This minus delta H vape over R, 1 over T 2 minus 1 over T. Okay. And so, for this problem, right, once we've established, okay, this is the equation we need to use, just kind of plugging things in, right? It's natural log of 350 over, P1, P2 is what we're solving for. P2, 1 is 350, okay. Minus delta H here is 43.99. That's kilojoules. This is going to be divided by 8.314 joules. Okay. I guess per mole, per Kelvin mole, right? And then the temperatures, right? I'm going to want convert these temperatures to Celsius, right? So 40, this is 338, I think. Kelvin, right? Minus 1 over 298 Kelvin. Okay. Now note here that this is 43.99 kilojoules, and this guy is joules down here. Okay. So you're going to want to convert the kilojoules to joules here. Oh, 313 Kelvin for 65. 273. Oh, okay. Oh, is that the final pressure, maybe? Is that what you're getting at? Oh, okay. Maybe. Right. And so, right, I'm going to have this natural log of P2 over 350 equals, right, minus, I'm going to multiply this by 1,000 to convert it to joules. Okay, so my units work out. Okay, I wrote all the units here just to show us, right, that in order to get these units to work out, either I got to convert this to kilojoules to joules, or this from joules to kilojoules. Okay, right, and then this, right, is again 1 over 338 minus 1 over 298. Okay. So I didn't do that right. Yeah, so yeah, I accidentally had to multiply instead of divide. That's my problem. Okay. 1,000 times 43.99 divided by. All right, so if I did my math correctly, I'll have the natural log of P2 over 350 equals negative 2.1. I'll just round it to 2.1. So that by 250. I don't know. If I did my math right here again, then take the exponential both sides and get P2 is equal to 350 times exponential minus 2.1, which, if I did things right, gives me 42.8 torr. Okay. Questions about this example? All right. Right. A couple other examples here. You can go over some of them. I think what we'll do, given time here, is next time we'll talk about electrochemistry. We won't get to electrochemistry today. But we'll do at least one or two more of these examples. But before we do them, I just want to mention, okay, that there's this equation. I'm not going to show where it came from or things like that, but this equation called the Van Hoff equation, okay, given here, which has to do with the change in the natural log of your equilibrium constant, expected change in 1 over temperature is related to this, minus delta H over R, okay, and basically, if you kind of do some math, integrate some things out, okay, you get this final form that the natural log of the K final over K initial equals minus delta H over R, okay, or it's delta H of the reaction times 1 over T final minus 1 over T initial. That form, which I'll go back to, right, should look familiar, right, because it's basically the exact same looking type of equation as what we have here, right? You have this natural log of pressures related with delta H over R times 1 over the inverse temperature, right? Okay, so this equation for the equilibrium constant, oh, wrong share, sorry. Right, this equation for the equilibrium constant, right, ln K final over K initial, how it changes with temperature is the same with that change in vapor pressure, okay, that we talked about before. And the reason why they end up being almost the same looking equation, the only difference is you know, you have equilibrium constant versus vapor pressure and enthalpy of vaporization versus the enthalpy of the reaction is, you know, the reason they're the same kind of form is because they're both those equations are related with equilibrium problems. Both of them, right? One, we're talking about phase equilibrium. Here, we're talking about chemical equilibrium, right? But it's both just equilibrium, okay? And so that's why you end up getting kind of the same functional form, okay, from these things, okay? And it's because they're both just related with equilibrium and how you know how your equilibrium is maintained with the change in temperature, which is related back to how the chemical potential changes with the change in temperature, okay, and so those relationships between chemical potential and temperature and maintaining equilibrium, right, is what gives us this Van Hoff type. I mean, this isn't called the Van Hoff equation, but you know, this equation for how the equilibrium constant changes with temperature, as well as that Clausius-Clapeyron equation that tells us how our vapor pressure changes with temperature. Okay, right, and the final form of this equation is just if you took the exponential both sides, you could write kind of this thing here, but you know, this is the version that I typically think of. Okay. Right. But yeah. So questions about this kind of equation here. Again, you don't have to know where it came from, where we got this Van Hoff equation, anything like that. But I just want to, you know, put out here, right, remind us, right, this is this relationship between the natural log of the equilibrium constants and temperature. Okay. And I know we're just kind of throwing out a lot of things right now, especially with thermodynamics. And part of that's just because the topics in thermodynamics, a lot of it is, you know, there's not really much to go on beyond, or that we want to go beyond in this class than what has potentially been covered in your undergraduate thermodynamic courses. But some of you potentially haven't had those in a while, or things like that, or maybe, you know, long since forgotten what was discussed. So we wanted to do kind of a review of some kind of important thermodynamic concepts. So again, that's kind of, you know, this topics on thermodynamics is all kind of reviewing, hopefully things you've kind of seen before, you know, and kind of when we get towards kinetics and quantum mechanics and spectroscopy and things like that. We'll talk about some other concepts and ideas that maybe we haven't seen kind of before. But all of this potentially is a review, just depending kind of on what ended up getting covered in your thermodynamics classes in undergrad. So again, any questions about this equation? We have time to do another example here. We did that one. That one's kind of a little bit more involved. Some equilibrium ones. This one, the answer is kind of written out in the slide, so maybe I'll don't worry about that one today. Yeah, so we'll do this example here, a little bit more involved one. Last 10 minutes class, right? So lab, you're in lab and you've, basically dissolved 0.001 molar CO2 into a 1 liter solution of water at 298 Kelvin. Okay, you know that CO2 in that solution, right? So you start off, you initially have 0.001 molar CO2. That CO2 in that solution of water can react with the water, okay, liquid gas here, right, to form H2CO3, right, strong acid, okay, right, and then after some time, once equilibrium has been established, right, you see a constant pH, right, that constant pH is telling you equilibrium has been established, right, no net reactions occurring in the solution anymore, okay, and you have, right, so at equilibrium, you have a pH equal to 3.12, okay, right, and we're given some other information here that will be useful for some other things, but right, we're told, for example, that for this reaction, the enthalpy change of the reaction is minus 12.5 kilojoules per mole, right? And then we're curious, what is, say, the entropy change of the reaction, and when would this reaction no longer be spontaneous, at what temperature, right? And some of the things we're looking at, okay? Right. And so for this, here, let me now switch. Okay, so, right, if I want to know, for example, what is the entropy change for this reaction, okay, right? Well, I'm told, right, for example, I'm told what the standard enthalpy change is for the reaction, right? I want to know what is the standard entropy change, right? One way I could potentially get that, right, if I think, well, what relationships, right, what can I get from this information here, right? Well, this information is related with equilibrium, right? So I might be able to get my standard free energy change for this reaction by calculating the equilibrium constant and doing this, right? And then I also know that the standard free energy change for my reaction, right, is just related with delta H of the reaction minus T delta S of the reaction, right? And again, this stuff is all taking place at 298 Kelvin, okay? And so this, right, information here, right, kind of shows me how I can get to my unknown here, my delta S of the reaction, right, I'm given some equilibrium information, so maybe I can get equilibrium and relate that to the free energy change. And then from the free energy change, maybe I can relate that with delta H to delta S, right? And so the first thing we need to do to kind of get this is figure out what is this equilibrium constant, okay? Well, we're told at equilibrium the pH is 3.12, okay? Which means, right, at equilibrium, right, concentration H plus is going to equal, right, 10 to the minus 3.12, right? 10 to the minus pH, okay? Which is what? This is 0.0076. I'll just round it there, molar. Okay. Well, if that's my equilibrium concentration of H plus is 0.0076 molar, right? To get to equilibrium, right, that means I had to react some amount of my 0.001 molar CO2, right? So at equilibrium, right, concentration of CO2 is going to be 0.001 minus 0.00076, okay, which is 0.000, no, 1, 2, no, that's order of magnitude. Oh, no, sorry. No, it is another 0, yeah, 0.00024. That's what I thought. Okay, I'm not going crazy. More, right? So now I have the equilibrium concentrations of H plus and CO2. Okay. So we can now calculate the equilibrium constant, right? It's just going to be constant, right? So this entire time I've been relating the concentration of H plus in my head to the concentration of H2CO3. Because H2CO3 is a strong acid, right? So that first hydrogen will fully dissociate. So whatever concentration of H2CO3 I form is going to equal the concentration of H plus I end up forming, right? I'm ignoring, right, the small contribution from HCO3 minus, right, that may or may not play in terms of determining the peak, right? I'm just kind of shoving off that side and just focusing on the fact that H2CO3 is a strong acid, right? So the concentration of H plus, right, is equal to the concentration of H2CO. Okay, that's the relationship I'm using here. Got to mention, right? So based on that, right, the equilibrium constant is just 0.00076 divided by 0.00024. Okay. Right. 76 divided by 24. This just gives us 3.17. Okay. And so plugging that in, right? I'm doing on time here. I'm almost out of time, right? But basically plugging that in up here, right? Then the ln of K times RT, or minus RT, right, is going to equal 8.314 times 298 times the natural log of 3.17, which ends up being 1.15, okay? So that gives you a delta G minus 2.9 kilojoules per mole. Okay, so that's what delta G naught is. Of the reaction, okay. And so then once I have that, again, I can plug this back into here with the delta H of the reaction to find out what is delta S for the reaction, okay? And then in terms of the question about it being spontaneous or not, right? This reaction is currently spontaneous, right? Delta G naught, the reaction is negative 2.9, right? At 298 Kelvin, right? So it's spontaneous at 298 Kelvin, okay? But the question is, when does it become non-spontaneous, right? Well, a reaction, right? A reaction is going to transition, right? So I have equilibrium here, right? If I'm spontaneous in one direction, right, delta G is less than 0, right? In order to get to non-spontaneous, right, delta G is going to be greater than 0. I reach a point where delta G equals 0 and I reach equilibrium, right? And so my reaction will change from being spontaneous to non-spontaneous when it passes through delta G equals 0, right? So if I solve for delta G of the reaction equaling 0, which equals delta H of the reaction minus T delta S of the reaction, right? And so basically that temperature in which I transition between spontaneity and non-spontaneity, right, solving for temperature here, right, is just equal to delta H of the reaction divided by delta S of the reaction. Okay. So this equation here, right, is going to tell me, right, this technically is like the equilibrium temperature, if you will, right? Above or below this temperature, you'll either be spontaneous or non-spontaneous, depending on kind of the signs of delta H and delta S, right? But yeah, right. And so yeah, so this is right your final equilibrium temperature, okay, right? And you should get in this problem up here, when you calculate delta S, you should get it to be a negative number. I mean, just looking at the reaction, right, that should be a negative entropy change. You're going from gas to, liquid to just one aqueous species and things like that. So you should get a negative entropy change for this reaction. But I kind of ran out of time to be able to solve for that number here in class. But questions about kind of this example here? By the way, homework has been posted online, so you can already go ahead and start checking that out if you want to, and start asking me questions about it if you have any questions. And yeah, otherwise we'll continue our discussion of thermochemistry on Monday, and we'll kind of finish it up then, and either just do a bunch more examples that day, or maybe we'll start kinetics. I don't know. Probably we'll just stick with just thermochemistry on Monday, finish up with our discussion on electrochemistry, and then just do a bunch of examples, some that we didn't get to today and other ones. Okay. All right. Well, we'll end the meeting here today on Zoom, and I will see you guys again on Monday.